Record. All right, so welcome. And we're doing our review for Monday, our celebration of chemistry, celebration of learning. So I just sent an email. So it'll be noon or 6 o'clock. So the noon time again will be the same. You just come to Zoom, and I'll be on Zoom the hour before each exam to answer questions. And I'll have a Sunday evening office hour this week too. But if you're coming at noon, if you're ready at noon, just come into Zoom and I'll email it to you. Otherwise, at 6 o'clock it will appear. It is a 2-hour limit because the classes always had less than 2 hours. And then there's a 10-minute window after 2 hours to get it submitted. So if you study, you'll be done in under 2 hours. The other big thing that I just emailed you about, I have notes to myself here, is about your demo presentations. So those will be Tuesday or Wednesday. You can worry about the exam first, but you might want to play with your demo this weekend. So if you want to change your mind, trust me, I get 2 emails a day of people changing their demo around. So you won't be alone. And I just realized I turned my lamp on. There we go. Well, maybe. And there we go. That's our blessing today's infinite blessings. So, and also a reminder with your demo. So besides doing a presentation, your presentation, I would recommend taking, depending on your demo, you can photograph as you go along, or you can make a couple of videos and then make a PowerPoint or Google Slides and embed the pictures, and then you'll be talking through it. I imagine these will be a little bit longer, like more like 10 minutes presentations, and you'll explain what's going on. And then you also have a write-up that you will be doing and submitting to me. And I posted a thing that you can look at. You can worry about that after our midterm. So it's thermodynamics and redox. And Erin and I were talking today. It does seem much better because we don't have the mice charts. So maybe that's why thermodynamics seems much calmer than in 221. And again, this is an old exam. So yours will have a similar format. And it will probably be more pages. It'll probably be 6 pages again because I'll give you more room to be able to write big or whatever. So entropy is disorder. I also recommend, by the way, going back and redoing your study sets. Both these study sets were our longest study sets because they just give you lots of practice. So maybe I did you a disservice by making your other study sets shorter. And a lot of you weren't practicing as much as you should have. And redoing your notes, you can rewatch the videos. All right, so first one, they are both gases. Look at the state of matter first. It is the C3H8. And then you will be telling me why. Just a real simple explanation. It has to do with complexity, structure complexity. And so there's more bonds, right? So there's going to be, yeah, the light does this. There's more bonds to vibrate and stretch and do entropic things. All right, the second one, they're both oxygen. We're looking at the temperature. So a higher temperature means more jiggles and giggles. And that also reminds me, I had put up for you guys last week that if you wanted to do the jiggle giggle giggleosis lab again this week and do 2 parts of it, so you're kind of like double dipping, and then you would write up what you've done on Monday. Hopefully it's made people have been more happy, it seemed like, in office hours, or maybe you just don't come when you're sad. But write it up and then you'll submit that on Monday also, and that will give you 2 bonus points to your exam. All right, so if you don't like my jiggles answer, the technical thing is there's more kinetic energy. So if there's more kinetic energy, of course, that's more entropy. So higher temperature is more jiggles, kinetic energy. All right, the next one, they're both sodium chloride. I'm going to pick the aqueous one. Again, we're making predictions. The aqueous is because the ions are meandering. So the ions are floating around, whatever verb you want to use. In a solid, everything's in a rigid structure. And that's actually what the word ions mean, actually, is meandering. So it's also a mixture. Aqueous means it's in water, so you have water and the ions. Sodium chloride, solid liquid gas, means a pure substance. I want to give a quick disclaimer there. When they actually measure the entropy, sometimes they get a different answer than our prediction, but these are predictions. All right, the next one. This should be bonus if anybody ever gets it. It is the H2S. So the real question is, why is it the H2S? And for me, in 222, I comment that one of the most important things you learn is hydrogen bonding. H2O does hydrogen bonding, which means H2S, this guy is the dipole. Remember a dipole? Just a quick review for the final. Next Tuesday, I'll be doing like a 2-hour review for the final during this time. There's actually another one of these. It's a little bit longer. So we'll go over some of the stuff from the past. So it is weaker intermolecular forces, which means you have more jiggles. So the weaker intermolecular forces, entropy means everything's moving around more. So the more jiggles, the more entropy. I know it's described as disorder, but I like the word jiggles because I have a chair that I'll probably break at home because I can jiggle in it. And so one of these days when I'm teaching, I'll really jiggle and the chair will break. That would be great, positive entropy. All right, the next one, the difference is the pressure. So ponder it for a moment. It's the lower pressure. So the high pressure is pushing it together. It's not allowing it to jiggle. So at a lower pressure, you can think of it a couple different ways. I've had people explain this various ways, but we would want the lower pressure would give it more movement, more disorder. At a high pressure, it would be compacting it is one of the other ways you can think of it. You can think of it as a volume thing. So a low pressure would mean a high volume. So there's more space to expand. So it's expansive. Like our hearts, that's why we're human. We have the expansive heart. All right. Or you can go with at the high pressure, it would be compressed. It would be all inward, which is good. Sometimes that happens. All right, the next one. You can read the story if you want. This is just, I'm not going to go through everything, but this is where you do the delta H of the reaction. Having looked at your worksheet, some of you were really skimping here. You got to show your work much better, which means stating the formula. So I will take the time again to state the full formula, which is, of course, the people probably skimping aren't watching this, but for those of you who watch this, so this is the sum, that sideways M or sideways W, whichever you see, and this is delta triangle heat of formation. I will give you, you won't have to use that big chart like you did on the homework if you actually did your homework rather than just copying mine. And if you did just copy mine, go back and redo it and do it yourself. So it will be the same for the entropy. We would punch in and solve. I'm going to do it for the enthalpy, the delta H, because I want to make sure you guys show your work. You would tell me you have 4 moles of the pH3 times the 23 kilojoules per mole. These are elements, the P4 and the H2. So by the way, P4 is a tetratomic. It's like hydrogen's a diatomic. Phosphorus is actually always found as 4 atoms when it's by itself. as enthalpy and free energy, they're zero. Everything has an entropy. So you do want to label. Don't just say 4 times 23. It is show your work. So you would get a number here, which is whatever 4 times 23 is, which is 92 kilojoules. I like to write after that that's endothermic. You would do all your work for your delta S. So your delta S comes out as 13 joules per Kelvin. I will leave that for you guys to walk through and do all your work, right? You know how to do your products minus reactants, showing your work beautifully like you did on the worksheet. The homework, I show it plenty of times. That is a positive also. They're both positives. If you want, you can show the sign, because sometimes that's helpful to see. They're both positive. That means disorder is increasing. That's a favorable condition. So as long as we have one favorable condition, we can make it work. For your delta G, you will very nicely state this formula also. Delta G equals delta H minus T delta S. When you plug in, you have to remember to change your unit from joules to kilojoules. And your temperature, pretty sure you all know that now, it is 298 Kelvin. So we would plug in our 92 kilojoules minus our 298 Kelvin, and then 0.013 kilojoules. So having been with many of you in office hours last night, you would hope I can do this step, changing this from joules to kilojoules in my head. It really doesn't take that much time to change it by showing the step. So just be careful that you move your decimal correctly. And you should end up with 88 kilojoules. And then I'm going to ask you what that means. It is reactant favored, and that is because delta G is positive or greater than 0. I didn't ask you to explain there. I'm just making sure everybody sees. It is not the endo and the disorder by themselves don't tell you if it's reactant or product favored. All right. So 2C has to do with exam 1, Le Chatelier's principle, temperature and pressure. It is endothermic. If we want to go forward, we want high temperature. Endo likes high temperature. So increase heat, endo is going to absorb it, and that's going to move it forward. For pressure, we are going to look at the moles of gas. So you're going from 6 moles of gas to 4 moles. So high pressure is going to push it forward. High pressure means you're pushing it together, so you're going to always push to the side with fewer gas moles. You're only looking at the gas. And so that's why I got high for both. There are several of you who are still doing that wrong. You're saying that these two are related. They are not. They're only related in a gas law problem, which is not this. This is all equilibrium and Le Chatelier's principle. All right, 2D. Again, I'm not going to walk through all the steps, but this is the delta H divided by delta S will give you the temperature. You can just state that. Remember, they have to be the same unit. The other way some of you like to do it, which is how I showed, is you can always go back to this formula and you set the delta G as 0 and you're solving for T. That's our unknown. Either way you do it, you will get the 7,077 Kelvin. If you give me that as your answer, you will lose a point or 2. Whenever you're solving for temperature on these questions with free energy, you have to tell me if we want high temperatures or low temperatures. But we just answered it in the previous question. Endothermic likes high temperatures. So you can, it's pouring down rain. I was trying to figure out what that noise was, and it's just pouring down rain here. So you can just put an arrow to say 7,077 Kelvin and above. You can write the word above, or if you're good with your greater than, less than signs, the temperature has to be above this. So the reaction actually will not happen here at room temperature. You have to get basically to the sun to make this reaction happen. All right, and of course you would show your work beautifully with your units and stuff. The equilibrium, delta G equals negative RT natural log of K. So rearranging, I am going to walk through this one, negative RT. And then to get rid of the natural log, we're going to do e to the power. I was approached by math many times in my first few years that I'm supposed to rearrange first with the variables. If you like, you can put your numbers in and then rearrange. I personally don't care, but you do state the formula. So we're going to have e to the power of, what was our G? Our G is a positive 88 kilojoules. And then we do have a negative there. I use 0.008314 kilojoules per mole K. If you use it in joules, this would be 88,000 joules. All right, and then the temperature, this is a question people are asking. If you use this temperature, your K is going to come out as 1, because that's the whole point of that. You always want to go back to the 298 Kelvin. You can ponder why. If you use the 7077 K as the temperature here, you would get an answer of K of 1. So that can be my bonus. I'm not going to give the answer. You'll have to email me and tell me, why would it come out always as the equilibrium constant is 1? You want to go back to standard temperature when you're doing the equilibrium constant. All right. The answer, of course, makes sense. K is less than 1. Delta G is greater than 0. That means it is non-spontaneous or reactant favored. A reminder, K is greater than or less than 1. We talk about free energy, enthalpy, entropy, cell potential, the voltage, we compare it to 0. They can all be positive or negative. Equilibrium is always a positive value, but it can be a large number or a small number. All right, questions on this first page?
I have a quick question.
Go ahead.
I was wondering, is it okay for us to write it as like when we're stating the equation, just to write e to the change in G over negative RT?
You can.
Okay.
I'm going to answer that. Yes, you can. There's a reason I didn't teach it that way. Well, traditionally it's given this way. Just be careful, Aaron, and anybody else who's pondering the same thing. That will work if you're going from delta G to K. There are times, there was one I know on the homework where I actually gave you K and wanted you to go and solve for delta G. So if you're starting with, there was on the worksheet, it was the KB, and all of you were like, what do I do with KB? It's just a special type of K. So if you know the K, it's easier to write it the original way. But yeah, absolutely, you can write it already rearranged like this, that is what K is equal to.
Okay, cool. Thank you very much. And yeah, and I get what you're saying. But it's nice to have a base to start from, just in case it's asked in a different format.
Well, also this would be really hard to type out in the format, and it would probably look scarier. All right, let's move on. So Hess's law. So my question for you guys here, I can pause the video and give you guys 10 minutes to try this page and then restart it. Do you want 10 minutes to play with it, or you want me to just walk on through?
I could try with the 10 minutes.
All right, I'll pause. All right, let's go ahead. So those of you at home, if you didn't pause me, you should pause me and try the page on your own. And Erin and I were just talking about good erasers and stuff. But this is all your own work. So this is Hess's law. And if you didn't love Hess's law before, hopefully you do now. And we're trying to get to this equation here, the one that we have the question mark with. And my equation, this first equation, the sulfur is what I want. So I'm going to flip my equation. And when I flip the equation, of course, I change the sign to a negative, change the sign, and then I'm going to double my equation because I need 2 sulfurs. And that means I would multiply this by 2. That's how I do it. I flip, I change the sign, then I multiply by 2. I know many of you came from other teachers, so they may have showed you different. This equation, what I notice is the 2SO3, so I look for the unique piece. And I want it on the product side, and I do want 2 of them, so there's nothing I do with that one. When I add my 2 equations together, I get 3 oxygens. What's up?
Oh, I just want I don't think your page is underneath the camera, is it? That might just
do you
be
not see it?
Yeah, for some reason I don't see it.
Marilyn,
can she see it?
I can't see it either.
You guys aren't seeing it?
Yeah, I only see the first page for the exam, for the practice exam.
What do you see?
Just the first page all filled out, and it's like frozen.
Oh.
Turn on it.
All right, I'm back. I apologize for those last 2 minutes. Apparently you guys couldn't see what I was seeing. I don't know why. Because I could see you guys wiggling, and I could see my screen. But, so again, the first equation we doubled and we flipped, so that becomes negative 600. And then we're going to add these together. And that's where I got the negative 740 from. So you will, it is show your work. And so you will have to show me what's going on, that you flipped it, you doubled it, or whatever, and that you're adding them together. So again, with delta G's, delta H's, we add. All right, number 4, you had one like this on your worksheet, and so I'm really happy this is on here. So let's walk through this. This is, the CO2 is this number. Oh, of course. So the CO2, I'm going to just write under them what it is. And my SO2 is negative 300 kilojoules per mole. All right, so I use those numbers up. And here's my equation. Sorry, the spacing didn't come out how it originally was. And then it tells you, there's a lot of words, the free energy change for the reaction. So that means the delta G of the reaction is the negative 1,059 kilojoules. So that's information given. This is the delta G of the reaction equals the delta G of the products, of formation of the products, minus the sum of the delta G of formation of the reactants. So many of you got the answer on the worksheet and got me replying to you saying, you know, you got to show your work. Everybody was like all upset when I did multiple choice, so you're showing your work. You got to show your work. All right, this is my delta G of reaction. That's going to go over here. This carbon disulfide is my unknown. That's what we're calculating, the free energy of it. The question is the oxygen. Delta G's of formation for elements are 0. So oxygen is going to be a 0. All right, my products would be 1 mole of CO2 times negative 394 kilojoules per mole. So this was a big question a bunch of people asked about the units. See that mole? See that mole? They cancel each other out. So that's why it's just kilojoules now. And then plus, we have 2 moles of SO2. And it's negative 300. So I'm pretty sure I'm preaching to the choir, because I'm pretty sure half of you showed me your work beautifully because you watched the videos and heard me keep repeating that you have to show your work beautifully. So please keep showing your work beautifully, and I'm grateful to you for that. And then we're going to say minus x. Be careful. In this one, we're okay to just say x, but if there were two carbon disulfides, this would be 2x. So this is the carbon disulfide. All right, you rearrange, right? You solve, and you'll get 65. So this is all adding and subtracting, so it's just moving by adding and subtracting. But again, that was a big question some of you had, is what happens to the moles? They will cancel. Technically, the answer is kilojoules per mole. Delta H's, delta G's of formation are per mole. The delta G of the reaction, the mole gets canceled out. That's a small piece, but several people have asked me, so I'm recording, sorry. All right, my door, we can see if my door can open and close anymore. That could be the question. How many times does Dr. Sherpa's door get slammed while she was trying to record? All right, so we're gonna write equations. This was in your notes. This was on the homework. This is on the review. This is usually an 8 to 10 to 12 point section of your exam. It might be even 15 points. This is huge. This is like the whole year. Can you write an equation and then discuss it? Vaporization of water means that we have water, it's a liquid, and we're vaporizing it, turning it into a gas. All right. So now we're going to do delta H. Predicting the sign, is it, you need to add heat, right? You're boiling water is what you're doing here. So we're adding heat. It's endothermic. It's a positive delta H. We're going from a liquid to a gas. It is increasing disorder, so it's a positive delta S. So when is it spontaneous? If they come out the same sign, it is temperature dependent. Two positives mean high temperature. You can also remember endo likes high temperature. If you have one favorable, which is the positive delta S, you look at temperature. The enthalpy is not favorable because it's endo. That's up to you if you want to use the happy and sad basis. All right, combustion of propane, C3H8. Combustion, I told you it's a gas, means plus oxygen. And you will get CO2 and H2O. You have a choice here, and I do look. You can go to H2O liquid, or you can go to H2O gas. We're going to have 3 carbons. We're going to have 8 hydrogens, so 4 H2Os, and that gives us 10 oxygen, so we'd have 5 O2s. Either way, the delta H is negative. Combustions are always exothermic, so that's a good piece. The delta S is going to depend on your states of matter. This shows me how much chemistry you know. If you made the H2O a liquid, this would be a negative. And it makes sense that would only happen at low temperature because it does come off as a gas and then it cools down at a lower temperature. If this is a gas, we then look, you have 6 moles of gas and you end up with more moles of gas. So in combustion, you end up making more moles usually. That would be a positive. So if you did all of them as gases, this is always favorable. So all temperatures. All right. So temperature decreases, calcium chloride dissolves. So dissolving means we're going from a solid to aqueous. So dissolving means we're forming ions. So we're just going to do calcium. This is calcium chloride solid, and we're going to make it into calcium ions and chloride ions. It's a KSP. Remember those? And they're always small. So this is not going to be a happy one, but it tells us if the temperature is decreasing, it's losing heat. So it means you're feeling it get colder. The temperature of the solution is decreasing. So exo or endo? I'm thinking for a moment. This would be endo. So this is a tough one, or to think about. The reaction itself is the system, and that's what we're looking for, the exo-endo. The temperature decreasing, what you are measuring is the surroundings. So it's like you feel it's getting colder. Maybe you're the surroundings and you're getting colder. The temperature is decreasing. That is because the system is pulling the heat from the surroundings. All right, so that would be a positive delta H. You can ponder that. It is moving towards aqueous, so that is a positive delta S. It's going towards disorder. And so we're back to high temperatures. If it's exothermic, the temperature will increase because you'll feel the heat given off. All right, that is different from how this one is worded, where the standard heat of formation is negative. This is the heat of formation that is telling you point blank the delta H is negative. And we're doing heat of formation. That means we're forming the calcium carbonate. So whatever it is you're forming, and you are forming it from its elements, which are calcium and carbon and oxygen. So CO2 is not an element. This is the weirdest question, I think, in chemistry, of all the bizarre questions in chemistry. Somebody just decided this is what it means, and so that's what it means. This is where you form 1 mole of the compound, and you're making it from the elements. So you balance with fractions. So the oxygen will be 3/2. We want to show our states of matter. The oxygen, of course, is a gas. The calcium, the metals are solid. The exception would be mercury. And then the carbon, you guys can just write solid. If you didn't figure out my other bonus point, you can try this one instead. Does anybody remember the standard state of carbon? It's not actually a carbon solid. You can ponder that one.
Something like graphite or something.
Oh, it is. There you go. Aaron already got that bonus point, so everybody's out of it now. Why you should all come to lecture, because then it's like you're part of class and you're not going to get behind. All right. We are taking all these pieces and putting them together. So this is a negative delta S. This is going to be low temperatures. So exothermic is favorable. The decrease in disorder is unfavorable. So this one is temperature dependent. All right. On number 6, we're just doing true, false. A is false. So we don't want to circle that one. The word always is the problem. So exothermic releases heat, But there is a possibility, which we saw like on the very first one here, where you have endothermic moving towards disorder at a high temperature, you can make it spontaneous. That's why A is wrong. B is wrong because it has to do with faster. There is nothing in free energy, enthalpy, entropy that has to do with speed. So you leave that one off. All right, C, that is actually what spontaneous means. That once it is started, it will continue on its own. So this is actually the words they use, that once a spontaneous reaction begins, it continues without external influence. All right. D, that is correct. So spontaneous, D and E would be right. So spontaneous, the delta G is negative, so the equilibrium constant is greater than 1, and E is positive. So those pieces all go together. The entropy, again, we can have the entropy change could be negative, but it can also be positive. We see that example up here. If the temperature is manipulated, instantly, again, has to do with how fast, which is not free energy. Spontaneous and instantaneous are not the same thing. And a catalyst, again, it changes the activation energy, which again has to do with kinetics, not with spontaneous. And I think that's it for spontaneous on the review. But again, go back over your study set and your notes. All right. Let's do, this is the last page, sorry. So I'm gonna pause again. You guys at home should pause and try these pages and pause.
Yeah, I figured it out.
All right, I'm resuming. Do you guys see my page, my half reactions? Or did I freeze again?
I see him.
Okay, so we are good. So I just went ahead and wrote out my 2 half reactions because that's pretty straightforward. The silver one's pretty easy. The electron is all we need for right now. Our other equation, we want to make sure we only have 1 carbon, and then you do the oxygen next. So you're going to need a water on the reactant side. So that gives you 2 oxygens. And then our hydrogens, we're going to need 2 hydrogens on the product side. And the hydrogens mean we'll also need 2 electrons because there were no other charges. All right. Now we have to multiply. So we just double. And then we add it all together. Oops. So H2O. It doesn't matter the order, HCHO, 2 silvers, the electrons have to cancel. We end up with 2 silver solids, HCO2H, and 2 hydrogen ions. The +2 is here from the silvers and +2 there, and we just have 2 oxygens on each side. So we're good. We can do our Leo-Gur also. My first equation with all the hydrogens, carbons, is my Leo, and then my second one would be my Gur. So down here, when I said in equation A, what element is reduced, that must have been the silver. And then the reducing agent would be the other reaction. It is not the water or the hydrogen. Those were there to balance. It has to be something that was originally, which is the HCHO. The carbon, by the way, is what is oxidized, which is fascinating. If you want, you can do oxidation numbers. It would actually be 0 because the hydrogens are +1. You don't have to do this, but it's a good review. So the carbon actually has an oxidation state of 0. On this one, the oxygens are -2, so that gives us a -4. +1, +1, so my carbon here is a +2. So that's why it's oxidized. It went from a 0 to a +2. That was a really quick review of oxidation numbers. You're not going to be doing that on your midterm, but you will have to answer a question like this. And we can see electrons were lost from our equation. All right, the mistake that is made on B. There are 2 arsenics. So if you did not put a 2, it never balances out. And I wrote my second equation really funny. I think that's when I was hearing the noise and I realized it was Aaron blowing away. Maybe it was Peter Pan coming to visit from your flow chart. All right, that should have been the manganese. So let's do our first equation. We have to do a bunch of, we have the 2 arsenics, and then we need another oxygen on the reactant side. And then we also need a hydrogen. Looks like 4 hydrogens. So we have 6 hydrogens here. I just did my oxygens wrong too. Sorry. So this 2 means I have 8 oxygens. So actually I need 5 waters. So let's do this right. So I have 8 oxygens. So here I have 3 plus 5 more. That gives me 10 hydrogens. So I need my hydrogens over here. This is why you want to do this in pencil or something that you can erase. So I think I'm good now. I got 8 oxygens and 6 plus 4 hydrogens. Now I can do my electrons. The only thing I had to charge were the hydrogens, so my electrons would be on my product side. I'm going to do it the way I taught in the class, which is I do it as if it's acidic, and then the last step I neutralize. All right, the Mn, there is 1 on each side. I need 4 waters on my product side, and then 8 hydrogens on my reactant side, and 6 electrons. Only 6 electrons, because the -6 and the +8 would balance my +8, and it's actually 5 electrons. I just realized I have a -1 here. I'm fascinated because these equations, doing them on paper, what I'm trying to teach and look at the screen, it's blowing my mind apparently. All right, I think I got it. So I have my hydrogens, my oxygens, and I need a net +2. So I have 6 negative and a +8, so +2 on each side. So my half reaction's good. You got to practice these so you feel comfortable with them. They do end up being people's comfort area. All right, this one's crazy because we have to cancel the electrons. So we're going to have to get to 20 electrons. So we're going to multiply the top one by 5 and the lower one by 4. So I'm going to have 25 waters, 5, 10 of the H3 ASO4, 20 and 20 electrons, 20 hydrogens and 20 electrons. And then my second equation, I multiply by 4, so 20, that is 32 hydrogens, 4 MnO4s, 4 Mns, and 16 waters. All right, now we gotta do one more step here. We gotta cancel some stuff. So the electrons have to cancel. Waters, we have 16 and 25, so 16 will cancel. This will leave me with 9. And then the hydrogen, 20 will cancel, and I will be left with 12. All right. It's gonna be fascinating. All right, so we have 9 waters. I'm gonna write a little smaller so I can fit it. 12 hydrogens. And then my arsenics, my 4 MnO4s. All right, then we have 10 of the arsenic acid, 4 manganese, and everything else got crossed out. And yeah, we're good. We're basic. So now we have to neutralize. So you have to neutralize the hydrogen. So we're going to add 12 OHs to each side. I'm just putting it in parentheses so you know it's not 120 H negatives. This does not cross out. this becomes 12 waters. Now the one we did the other day, there were the H2Os were on the other side, so they started canceling out. Here they're on the same side, so they're going to combine. So our final equation, we'll do it in green. 12 plus 9 is, oh bummer, the airplanes are flying over now. They were not flying over this morning. It was so peaceful. All right, 21 waters. I also pondered maybe people stopped buying stuff, and then I was like, no, it's not going to happen. Not yet, anyway. All right, so 21 waters, 5 arsenics, 4 manganate, permanganates, 10 arsenic acids, 4 Mn plus 2s, 12 hydroxides. Let's hope it's balanced. All right, let's check the oxygens. Wow. A lot of arsenic. I wrote this wrong, ASO4. All right, over here, I have 21 oxygens. I have 5 times 3, which is 15, and I have 4 times 4, which is 16. So what is that? 11, 12, 52 oxygens? Oh, good, I have 52 on the other side. That's a crazy number. That's because I have 10 times 4 plus 12 more. So I have 40 plus 12. So I'm good. My oxygens are 52. So it must be right because that's a crazy number. Let's look at the charge. On this side, my only charge is the 4, -1. So I have a -4. And then on this side, I have 4 times plus 2. So that's plus 8. And then I have 12, -12. When you add that together, you get -4. So if you got it, that's like, again, the virtual high five. That's awesome. That was a really good problem to do. Again, do a whole piece of paper. Don't write as big and crazy as I did initially. I realized that was in pen. We want to answer the questions about what's oxidized, reduced. That's going back to your half reactions. My arsenic is my Leo, my manganese is my Gur. So what was reduced is the Mn. So again, it is an element that becomes reduced. It was the manganese that changed. Reduction historically meant reducing the number of oxygens. So the Mn lost oxygens. I don't know. Sometimes that works. And then the reducing agent is on the other reaction, and it has to be on the reactant side. So it is the AS2O3. Put the solid if you want, but there we go. Whew. All right. Hopefully I'm recording. I don't want to do that whole thing again. Hopefully you guys can see it. All right, our gnome, you two are doing good. Unicorn the gnome, we're going to move with us here. You know, this note, this was a talk I listened to from the Dalai Lama, and he said the 3 most important things in life is compassion, that's the whole Tibetan Buddhism thing, kindness, and to have a sense of humor. And he's always smiling. And when he laughs, he always jiggles. It's pretty awesome. All right. 2 similarities and 2 differences. Big difference, electrochemical is spontaneous. That is the battery. Electrolytic is non-spontaneous. If you want, you could say it even more simply, negative E and positive E. That's all one reason. That is a difference. That is the big difference. What's another difference? You guys know these. So 2 cells versus 1 cell. The other big difference, to me that's kind of a wimpy one, but that is actually important, that is the electrodes. The cathode in electrochemical is positive. In electrolytic, the cathode is negative. I was going to say something else now. Oh, you know, it goes with the spontaneous and the non-spontaneous. So non-spontaneous means that you have to plug it in. But that actually goes with saying it's non-spontaneous. But just a reminder, when you draw your electrolytic, you would show that you have to plug it in. I did that in the lecture yesterday, and it's your first question on your worksheet today. All right, so let's do the similarities. Similarities is Leo is always at the anode. Now you can't say the second one is Gur is always at the cathode, because that goes with what Leo is at the anode, Gur is at the cathode. That is one thing that they have in common. You could also say, so the anions are always flowing towards the anode. So that was the definition of the anode, is oxidation occurs, or the anions flow to the anode, and that was where oxidation occurred. We could go the opposite, Gur always happens at the cathode, or the electrons always flow to the cathode. So there's that path of flow of charge. You could also say the cations flow to the cathode. All right. The reactions at the cathode and the anode, this is when an electric current passes through. This is actually the question on your worksheet. The key is you're starting with ions. The cation is at the cathode. The anion is at the anode. The cations are positive, the anions are negative, but the cathode is negative. And so the cathode is Gur. We're gaining electrons, and you're going to go to the elements. Electrolysis. So in nature, all elements except noble gases are found as ions, and then there's also the noble metals, which make them special. The chloride is going to, the anode loses, so it's going to go to chlorine gas, plus its 2 electrons. All right. So again, anode means losing. So you're making the elements. You're going from ions back to the elements. So you're forcing the electrons back to where they were. We're going against everything we learned back in 221, 222, where we wanted to donate electrons or gain electrons. We're forcing them back. All right. So we're doing chromium. We're going to take 1.35 kilograms. Chromium is Cr. We're going to do it as factory label. It really is much more efficient. I am going to get rid of my kilogram here because I'm not asking for kilojoules anywhere. So kilogram to grams, and then your periodic table, 52 grams of chromium to 1 mole. It is chemistry. So that's where the periodic table, this is where this whole factory label is for unit conversions, the periodic table. Chromium, it tells you right here, it's chromium 3. So for every 1 mole of chromium, I will have 3 moles of electrons. And again, that's the charge. So Alexander, if you're listening, when you listen, here's an example where it's not 2. But I told you the charge there. Your next step would be Faraday's constant, a mole of electrons to 96,500 coulombs. And then the other piece of information, so if I forget to highlight, just you can ignore all the words and just find the pieces you need, is the 2.25 amperes. But the unicorn came along saying you shouldn't ignore flying over the North Pole on a unicorn. Except there'd be a lot of smoke right now from the fires in Siberia. So amps. So this was a question somebody had asked me, 2.25 amps. That means that you have 2.25 coulombs per 1 second. When we use this in the factor label, we flip it upside down. So we say there's 2.25 coulombs in the denominator and the 1 second on top. When you punch it in, you're going to get a crazy huge number. And so, oh, I asked how many days. 3,600 seconds to 1 hour, and there are 24 hours in a day. It's a unicorn. He can fly all day long. He doesn't need a break. You might, but you'll probably fall asleep. And 39-ish days. Questions? If not, I'm going to pause to give these folks a chance to try some. You guys should pause at home. Probably.
Following
Okay.
along.
Okay, you're good. All right, we're back. So this question, I am pretty sure in your homework you will see a question like this. I know on the final there's a question similar, and I know on your midterm there is, where I give you a box, and then a question will be asked. So these are all reductions. These are all gaining electrons. If they are gaining electrons, that means they are oxidizing agents. So remember, gaining electrons is reduction. It's causing something else to go through oxidation. What that means is the reactants are oxidizing agents. The numbers, this would be my strongest at the top to the weakest. That is gold 3 iodine hydrogen ion, okay? The opposite is true if we flip the equation. So the other side of the equation is the reducing agents. So the products are actually reducing agents, and the strongest would be at the bottom. It is, excuse me, to the weakest. It's similar like when we did acids and bases. The stronger the acid, the weaker its conjugate. That happens with the oxidizing agents form a reducing agent. The stronger the oxidizing agent, the weaker the reducing agent. So with that, which is the strongest oxidizing agent? That would be the top left of the chart. If you write gold, you will get it wrong. It is gold +3. The strongest reducing agent would be on the bottom right of the chart. It is the zinc solid. What oxidizing agents can oxidize I negative? So the I negative is here. It's telling us we have to flip this equation. The only thing capable of flipping this equation in my chart is the gold. So the gold is the only one that can do it. If I'd asked like about the zinc solid, it would have been all 4 of these above it. All right, and then it says, can gold I know the answer is no, because, so it's asking gold to be the reducing agent. We just said gold's the weakest reducing agent. So gold is too weak to do that. So the answer is no. Again, there's one of these in the homework. I can't remember if there was one in the notes. I don't think there was. But go back and look at it. And actually, you know, it was a discussion we were having earlier, Aaron. A huge advantage you guys have is when you get tired in class, you had to keep taking notes. On a video, you guys can stop me and go do stuff and come back. You just have to have discipline to come back. All right, this is, we're going to need that chart. And, all right, let's see, we have it here. We're doing tin and zinc. So actually, we don't need the chart from our notes. This would be like, this was an old exam. That's what I was thinking. The chart, this whole page goes with this chart. The chart is up here. The one that is higher on the chart, you write the equation how it is. So we're going to do it as the tin plus tin 2 plus the 2 electrons to tin solid. And that is negative 0.14 volts. The lower one gets flipped. So zinc solid going to zinc ion plus electrons. And when you flip the equation, You change the sign to positive if it was negative, vice versa, and then we just add them together. Again, I do this different than the YouTube videos. My way is much better. In a test situation, you don't confuse your brain. Your teacher teaching in front of all of you doesn't have to confuse her brain. All right, that's our E net, is the 0.623 volts. You would lose a point if you kept going at this point because I wanted you to write the full overall equation. So let's go back and finish. Those are the two half reactions. The full equation would be the tin plus 2 plus the zinc solid. The ions nicely canceled. We had two electrons, I'm sorry, the electrons canceled. And then we'll end up with the zinc ion plus the tin solid. All right, let's go back up and label our two half reactions. So my tin is my GR, it's gaining, and my zinc is my LEO. That's going to allow us to answer the next question. LEO is the anode, so zinc is my anode. The cathode, this is electrochemical. I told you there. So the cathode is positive. The electrons flow from the zinc to the tin. So LEO is losing electrons, so my electrons are flowing that way. So the anions are going to be the other way from the tin to the zinc. If you write your half reactions and label, you've got this, and then you move on. You've got to practice so that you can just do it. All right. I'm not going to solve this whole thing. This is just E equals E naught minus the 0.0257 over N times the natural log, and we're going to write our equation out. Our Q is products over reactants, so it's zinc and the hydrogen on top, and the hydrogen ion squared in the denominator. I ignore the zinc solid. This is not the question we just did in number 11. We have to figure out our new potential. But that's pretty easy. The hydrogen is 0. And then the zinc, we flipped it. So my E naught is 0.763. We're solving for E. I guess I am going to show the setup. N is the electrons, which is 2. 2 hydrogens, or the zinc has a +2, so there's 2 electrons. And then there's a natural log. So the zinc is 1. The hydrogen is 0.5. You can leave the units out once you plug in here. And then the hydrogen is 10 to the negative pH. So just a reminder, 10 to the negative pH is your hydrogen. That, 3 weeks ago when I did that the first time, people were always scratching their head. The biggest mistake made here is you got to remember to square it like that. And you would just punch in, and we get this as our answer. All right. So I'm going to keep moving because you're going to explain why the answer makes sense. So the big change is the pH again. Talked about yesterday. Standard pH would be 0. Standard is 1 of everything, 1 molar, 1 atm. So yeah, we did change the pressure, but the pH is a much bigger change. So a pH of 0 to 1.84, that's almost a 100-fold change. So we increase the pH, which means we decrease the hydrogen. Hydrogen ion is a reactant, in this case, it's right up there. So we're going to shift reverse. That's going to make it less spontaneous. That's going to decrease our E value, which we see it's smaller than the initial chart value. So again, the change of pressure or pH or concentration, that is the cause. That causes a shift to happen. If it shifts reverse, it's less spontaneous. If it shifts forward, it's more spontaneous. So you always want to start with the cause, shifting, and creating our effect. All right, Erin, this is actually the question from earlier. I gave you the K here. So delta G equals negative RT natural log of K. You would just plug that in. We'll get a number. To solve for E, we would do delta G equals negative NFE. You guys can pause and do it at home. The number of electrons is 2. We can see that there. You know what's really interesting about this, I don't know where this 2 in front of the mercury came from. That's a mercury 2 ion. Faraday's constant. The biggest thing to be careful of is delta G's. Depending on your R you use, make sure you stay in the same unit of joules or kilojoules. So if K is less than 1, delta G should be greater than 0 or positive. E should be less than 0 or negative. You can either say less than 0 or you can just show the sign. And it makes sense. My delta G came out positive. My cell potential came out negative. So hopefully you pause me. And so when it says does it make sense, that was all of this. They're all telling you reactant favored. Or non-spontaneous. And a reminder, non-spontaneous doesn't mean it can't happen. It means you just have to keep pushing. All right. So again, test is Monday. I will have office hours Sunday night or Monday before each test. And same as before, I'll be on Zoom. So if you have a question, you got to practice. You got to do your homework. You got to get your stuff in by Monday. And yeah. And infinite blessings. I'm going to stop. All right. I will see you all very soon.